All right. Hello, everyone. We have arrived at the last class where I teach you new things. So, yay! Two more classes, including this one. This is the last one with any kind of clickery stuff. Tuesday will just be a review. We'll go through the things. I need to send an announcement. I'm not going to be in town Friday and Monday. That means no office hours Monday. But in return, on Tuesday, I'll do open office hours from 11:30 to 2:20. So I'll just so I'll be around for those 3 hours on Tuesday. And then on finals week, so your all's final is Thursday, December 5th, from 1 to 3:50. From 1 to 3:50. I don't know if did I show you all the UCF exam website? No, probably not. All right. If you all didn't know, this is something very useful to find out in the beginning of your UCF career. UCF has a website where all final exam schedules, this is actually how they disseminate the information. So this is how I find out. I go to this website a couple weeks into classes, and you just put when your class meets. So Tuesday, Thursday, we meet at 3 p.m. and our class ends at 4:20 p.m. So UCF every semester has a fun optimization thing of scheduling all the exams and making certain there's no conflicts. Our class does not normally meet for 2 hours and 50 minutes, so they have to make it work. Hence why it's 1 to 3:50 instead of 3 to whatever else it be, I guess. 3 to 5:50, I guess, but it's not that. So anywho, this is true of any of your classes. Now, the exam will be in this room. That's also a rule of thumb with all your exams. They'll be in the classroom that you have the class in because they have to fit you all. So the alternative is they'd have to find a room that can fit this number of students, and that's a whole logistics nightmare. But yeah, I don't agree. I don't know. I assume someone wrote some code at some point that does this, but it's probably a really interesting thing because that makes sure there's no conflicts with any of your other classes. And that changes based on major and room and all the things. That makes sure there's no conflicts and that there's no conflicts with this and another class, as far as this room getting used. And yeah, it's an interesting problem that I don't have to solve. So there it is. To that end, like I just said, so I don't think, no, it doesn't show a calendar. The Monday and Tuesday before this exam, I will have just open office hours from 10 to 2. On that Monday, 10 to 1:30 on Monday, 10 to 2 on Tuesday, and then 1 to 3. I'll send out an announcement. So they'll be longer. I'll be there, pop in, or don't, up to you. I'll be there either way, working on things if no one's there, or helping people out if people are there. So yeah, lots of opportunities to get kind of last minute help. I reached out to the grader for test 2. I haven't heard back. I just sent him an email today. So if I hear back from him tomorrow, there's any delays or anything, I'll let you know. But I did, my other class, different grader, they finished, and the average was an 80% on the free response, and it was a very similar free response, so I expect the same to be true for you all. The first free response question was pretty straightforward, conservation of energy, and just from the handful that I've graded a few for that class and for this class. And pretty much the vast majority of people did that. If you realized it was conservation of energy, you got all the points. If you realize the first problem was conservation of energy and you're good with those problems, it was a fairly straightforward problem. The second problem wasn't bad. Less people were less likely to choose it. It was both conservation of energy and work. I'll go over those problems on Tuesday, whether or not I get the responses. There you go. That's that. That's the update on all those things. The last quiz will open tomorrow, and it'll be due the Wednesday at midnight. It'll be due December 4th at midnight. So you have tons of time. Very bad decision to wait until December 4th to do that quiz, though, because there will be questions on the test. And do you really want to find out the night before that you don't understand rotation? That is not the ideal time to figure out that you don't understand it. The purpose of the quiz is really as a checkpoint for you all. Do you understand it? There is a problem I'm going to do today with you all that is I don't know, I want to say it's tricky, but there's something in it that I made a mistake on, and I didn't realize this mistake till a few days ago. Another instructor pointed out to me, and I was like, oh, yeah, that's true. And fun fact, when you put the problem in ChatGPT, it also gives the wrong answer. I made this problem before ChatGPT. Before I started using ChatGPT, but it was one of those fun things that if I make a mistake, I guess ChatGPT also makes a mistake. I don't know. Makes me feel good, I guess, on some level. But we'll do that problem today. There's going to be a problem like it on the quiz. So it'll be the last thing we do. It'll literally be the last problem we solve. It's, where is it at? This one. It's not a terrible problem. We're gonna have to do a bunch of writing for it. It's not a terrible problem, but there's just a little detail in it that catches people, including me. So, yeah. Today should go really smoothly, though. We actually don't have that much left to cover. Yeah. If you all stop by during my office, I'll show you any exam you want. Yep. So last class, we did a few things. I told you all about moment of inertia. So where's that? There it is. Integral of r squared dm. The farther you are away from the axis of rotation, the harder it is for you to accelerate. That's what this moment of inertia is. It's really hard to move things that are far away from the axis of rotation. And finally, someone requested demo duck. It actually works out really well. Demo duck is pretty simple to spin in a small circle because it doesn't have to move that far. But if I want to spin demo duck in a really big circle, I guess it's fine, but it's a lot more strain to kind of spin something in a big old circle at the same kind of rate. It's hard to speed things up when they're far away from you. You can experience that for yourself if you want. Try to spin something. And this is the kind of math reason why. This is the math expression that represents that. Moment of inertia, it's like mass for spinning. It's how mass is distributed. And then I gave you all some shapes and said, here's the moment of inertia, about a bunch of random shapes. You don't need to have any of these memorized. If you need to know the moment of inertia of a shape, I will give it to you. That's a rule of thumb. So if you need a sphere, I'll give it to you on a test. If you need a cylinder, I'll give it to you on the test. So on and so forth. But this was to show you that you can calculate them, though it is a triple integral or a double integral, depending upon the shape. We will do a calculation for one of these, kind of, sort of. We will do a thin rod, a variation on the thin rod. In fact, we already kind of did it. Using the parallel axis theorem is how we started. I showed you all this is the easy way. If you know the moment of inertia of an object and you shift the axis over by some distance d, the new moment of inertia, so this is the problem that we did as a clicker question. A sphere about the center is 2/5 mr squared. What's the moment of inertia instead if I'm spinning about the side of the sphere, or rotating about that side? And it's shifted over by r, so you just add, in this case, d is r, so you just add mr squared, and it's awesome. And then we did this one, where the moment of inertia about the center is 1/12 ml squared. We shifted it over by 2l over 6. That was the challenge. You can figure that out. And you get the new moment of inertia of 7 over 36 times ml squared. And this problem's so much fun, we're going to do it again, but we're going to do it with the definition of the integral of moment of inertia. So that's kind of parallel axis theorem. It's great. It makes your life so easy. No integration. You just add, you just figure out how much it shifts and you add md squared, and it's easy. So easy. What I need to teach you all now is we're going to do this one. Find the moment of inertia of a rod with mass m and length l, and it's the same problem, but we're going to do it with an integral. Now, to prepare for that, so we're going to go over how the heck do you integrate these things. And this is basically going to be our example to show you how you integrate it. So, remember lots of things on here for now. Just focus at the top. The top is that's the definition. The moment of inertia is r squared dm. That's just the definition. That is how you find moment of inertia. The problem is, what if your mass is located at different r's, which is pretty much every object? Then an r is not a constant, so you can't just pull r out. And how the heck do I integrate r squared dm when dm is a function of r and I got to figure that out? we're going to do it the same way we did center of mass. Center of mass, if you all remember way back when we did center of mass, so our center of mass was 1 over the integral of dm times the integral of r dm. If you all look at these integrals, they look really like r dm is just missing, this one's just r squared dm. We're going to use the exact same trick to do this integral that we did with center of mass. We're going to get m in terms of r. That's the goal. So how do we do that? The same way we did center of mass. We said, man, if only there was a function that told me how much mass I had given where I'm located. And that is called the density. So remember, y'all, that density, this little p here is supposed to be rho. For three-dimensional objects, p is mass over volume. If you have a one-dimensional, we replace it with something called lambda. When I taught you all center of mass, I just kept it as rho. If you want, keep it as rho. So we can instead do this, instead of a volume, we could do a length. Density is just how much mass, this is a linear density, how much mass per length of the rod. If it's a one-dimensional object, it's that. There is a surface density, that'd be mass per area. There's a volume density, it's mass per volume. Depends upon your object, if it's 1D, 2D, 3D. Again, I don't know. The question that might come to your mind is, what the heck, one-dimensional objects, do those even exist? You can approximate a straight line as a rod as a one-dimensional object. Like, approximations are always a tool. Anyway, so we just, rearrange things. So I'm using lambda here. Lambda is kind of the symbol that we use for one-dimensional density instead of rho. So these two things are the same. This is just kind of notation. And you just shift things around. Move the L to the other side. So you get lambda times L equals M. Then just take the derivative of both sides. Derivative of both sides, and you get dm equals lambda dl. And I don't have room for that, but you can see that here. Just take the derivative of both sides, rearrange it. It's the exact same thing we did for center of mass. So the long and short of it is that we're going to consider that this density is a constant, make your life a little bit easier. If it's not, it stays in the integral. Lambda, integral of r squared dr. Really nice, really straightforward. You just integrate r squared. Okay. So this is for a one-dimensional object. If your object was two-dimensional or three-dimensional, you'd have to integrate with both dimensions. And you'd have to change r into whatever coordinate system you work in. And it'd be a heck of a fun time that you unfortunately don't get to experience. So sad. All right, so let's actually apply this. Anytime there's a new equation, it makes way more sense when we actually start using it. So find the moment of inertia of the following rod. This rod has a mass m. It doesn't specify that, but I'm just going to tell you that's the case. By direct integration, i.e. do the integral. So what's given? There's not really, to call this a given is questionable. There's not really a given, so we're just going to jump to kind of step 2. Step 2, we are finding I. I is question mark. Step 3, I equals the integral of r squared dm. That's just like the classic equation. And then we're going to do that, replace it. We're going to replace it with the thing I just taught you all, that we can replace that dm. So dm equals lambda dr. We just derived that. That's just, if you multiply density times length, you get the mass. At least a very, very, very tiny amount of it. Okay, so great. There's the integral. Now the challenge for you all, the part that I'm going to let you all practice, is what are the bounds of my integral? This is a definite integral. We are not integrating from negative infinity to positive infinity. Does that mean I had a rod that stretches to negative infinity and a rod that stretches to positive infinity? We have a rod with a finite size, so you need to decide what the bounds are. I'm going to give you all a few seconds, then a few moments, then I'll give you a hint, and then I'll give you a few more moments. See if you can guess what the bounds are. right, so my hint to you all is R is a measure from the axis of rotation. R is measured from the axis of rotation. That's kind of like my origin. So we got to make sure we get all the R's. We got to integrate from the farthest thing to the left to the farthest thing to the right, and everything is measured with respect to the axis of rotation. That's my axis of rotation. All right, so the grand reveal, what is the limits of the integral? The limits are negative L over 6 to positive 5L over 6. It is very, very important that you put basically it's how far to the left am I, that's my lower bound, and then my upper bound is how far to the right. That way I'm integrating over the whole object. Now, why is it negative L over 6? It's because it's to the left. And it's easy to explain why it's not positive L over 6. That's actually makes it a little bit easier. If it was positive L over 6, you'd instead be integrating a rod that looks like this. You'd be integrating a rod that isn't actually touching the object, that has some distance. It starts at L over 6 and ends at 5L over 6. If you did that integral, that's the moment you'd be doing the moment of inertia of this awful shape I just drew. I say awful, it's just a little scribbly. Obviously, our shape's got this extra bit, so we got to account for that. So negative L over 6 gets us, positive L over 6 gets us the whole thing. Okay? So you just got to make certain you get the whole shape. Man, this thing is not worth it. All right, I keep trying to use presenter mode because I think it's nice and I think it makes it easier. And the reality is it just ends up being a pain in the butt. So back to good old classic where everything works right for me and the stream breaks. Boop. Okay, back to good old this. Okay, so do it. Do the integral. You can do this. It's not a hard integral. Do it, plug it in. We know what the answer is, y'all. We've already done this problem. We know the final answer is going to be 7 over 36 ml squared. This is the exact same problem we did before. So we know the answer. It's 7 over 36 ml squared. So we get lambda r cubed over 3 from the bounds L over 6 to 5L over 6. And then really the hard part, the integral is the easy part. Now you got to plug those in and simplify. So lambda, I guess I could pull out the 3. Lambda over 3. So 5 cubed is going to be 125. L cubed over 6 cubed is a number. Is it? It's not 250. What is it? What's 6 cubed? 216? I'm hoping that's what. Can someone confirm 216? It is 216. Great. All right. Okay. So that's the first one. And then we get minus, and you get a negative because it's cubed. L cubed over 216, so that turns into a plus. So we get lambda over 3 times 126 L cubed over 216. And you say, that's really nice. I need more space. Where's my beautiful picture? Up you go. Problem. Up you go. Okay. So then it's just algebra. Algebra never hurt anyone, right? So you get lambda. Well, let's just pull out the number. 126 divided by, what is 3 times 216? $648 over 126. Okay, and you're looking at this. 126. This does reduce to 7 over 36. You can test it for yourself. Both are divisible by 18. They both share a multiple of 18. And you may be like, how the heck am I supposed to figure that out? Generally, when you're simplifying a fraction like this, you just pick the easy ones. They both divide by 2. That's a good place to start. And then you might eventually realize they both divide by 8 after that. And then that's 16, and it all works. Great. Okay. So prove that to yourself. Prove that to yourself. And you look at these and you say, yep, that's totally not the same thing that we have written in the top right. This one is lambda L cubed. That one's ML squared. And this is where we get to review, do you understand what density, that this is density? And do you understand the relationship between density, length, and mass? So this is a good reminder. Lambda is my mass per length. That is the definition of density. In this case, a linear density. So, if I rearrange this, the density times the length gives you the mass. So, just pull out an L. And ta-da! It turns into mass. Yay. Isn't that nice? So look at that. Even though we didn't know the density, we didn't need it. It turns into mass. So that's the kind of nice realization here. In any moment of inertia, you have to work with kind of this density thing, and then it ends up getting converted back into mass again. So, yeah, and that's how you get a moment of inertia, and it's way more work. So hopefully now you have an appreciation. This was really easy. We just added md squared, and that took us 30 seconds or a minute or something once you realize how much it moves by. This one obviously took us more time because you got to do an integral and a bunch of algebra, and parallel axis theorem is great. Parallel axis theorem is really, really great. It makes your life way easier. Almost every object can be broken into a rod, a sphere, a plane. So if you know the moment of inertia is a really common objects, you just figure out where the axis of rotation is. You can use parallel axis theorem for almost anything. It's really, really nice. So there you go. Moment of inertia. Woohoo. Moment of inertia is, in my opinion, the only new thing I'm teaching you all when it comes to rotation. When I say the only new thing, everything else has just been a new paint job. Remember, all the rotational variables just kind of get swapped for translational variables, vice versa. This is the only new thing. At best, I can compare it to center mass, but mainly just do the math. So this is the trickiest part. Now it's done. We did it. And now we get to go back to just, hey, let's look at physics equations that were for translational and compare them to rotation. So I already mentioned a few of these. So rotational kinetic energy. Remember, regular kinetic energy is 1/2 mv squared. Rotational kinetic energy, you just, everywhere m is, you replace with an I. This is the reason we need moment of inertia. Everywhere mass is, we replace with an I. Velocity gets replaced with that. Whoa, now we got the kinetic energy equation for a rotating object. If you want to find angular acceleration, remember Newton's second law, F equals ma. We're just going to replace F with torque, replace m with I, and a with alpha, and it's the rotational version. You want to find angular momentum? You do the regular momentum equation. You replace momentum with angular momentum. You replace M with I, and you replace V with W. Every single equation I've taught you, there's a rotational version of it. Every single equation I taught you, basically, there's a rotational version of it. The variables just get swapped out. Everywhere M is, gets replaced with I. Everywhere A is, gets replaced with alpha. Everywhere V is, gets replaced with angular velocity, which is omega. And it's great. And again, there's like this L, that's just angular momentum. There's this tau, it's analogous to force. So that's the one we're going to actually practice now. Well, I'm going to give you kinetic energy, and then we'll get to that one. So, time to do a problem that you're not going to like. It's a really simple problem, but, well, I say simple, the wording's simple. All right, which will reach the ground first? A 5-kilogram block sliding frictionless down a ramp, or a 5-kilogram sphere rolling without slipping? Now, for something to roll without slipping, there's friction. So I got a block going down a hill without friction, and I got a sphere rolling down a hill with friction. Which reaches the bottom first? Block, sphere, or safe time? Assume no air resistance. I'm going to tell you all the trick to this is it's an energy problem. So we're going to set up conservation of energy. I'll start doing that in a second. What energy do they start with and what energy do they end with? All right, so I'm going to leave it open while I'm solving this. So they both start with the same energy. They both start with potential energy, and that's it. Remember the bread and butter, y'all. Energy initial plus work equals energy final. And then we look at the work. So that's the only energy they start with. There's no springs. Neither of them are moving to begin with. Neither ones are rolling to begin with. And then we ask ourselves, is there friction acting on these? For the block, it says, no, there's no friction. So there's no friction in the first one. And then the thing that's crazy is the sphere does have friction, but it does no work. A rolling object that doesn't slip, friction actually does no work to it. Friction only matters when things slide against each other. A rolling object, an object that's rolling perfectly without slipping, friction is actually a completely good thing, and it actually lets it roll. If there's no friction, it can't roll. But when there is friction, if it's rolling without slipping, friction does not do any work on it. It doesn't take away any energy. That's why wheels are so great. Wheels let us ignore friction, which is really nice. So actually, there's no work done on the rolling sphere either, because it's not slipping. If it slips, then you lose energy. So your tires, when you're driving a car, if you've ever driven it, your tires tend to every now and then slip. If you hit the gas too much, they spin in place a bit. That's lost energy. If you hit the brakes really hard, your tires skid, then yeah, that's friction happening. And there's a little bit more complexities. But in general, if we assume something's perfectly rolling without slipping, no energy lost to friction. All right, what does it have at the bottom? Kinetic energy. Neither of them have potential energy. But they're both moving. Both objects are moving at the bottom. So they get kinetic energy. And then the new thing is that the sphere also has rotational energy. So I'm going to leave that there and then let you make a decision based upon that. Given these setups, which one will reach the bottom first? All right. In 5, 4, 3, 2, 1. Boop. And the answer is the block. Yeah. And you may look at this and say, what? Why does the block make it to the bottom first? All right. The block, look at these equations, y'all. The block gets all the energy goes to translational motion. And the faster you're going, the quicker you're going to get somewhere. The sphere loses energy. Some of that energy is actually in the rotation. So this term, the velocity has to be smaller because literally there's something else being added to it. They both start with the same energy, but for the rotating object, some of it has to get shunted to the rolling motion. And then you may be like, what's the point of wheels? It's because friction exists. Like, the key here, the reason this is a weird problem is you're never going to find a frictionless surface. And in fact, if it was frictionless, the sphere and the block would reach the bottom at the same time. If it was frictionless, they would actually both slide. Things only roll if there's friction. If there's no friction, a sphere is not going to roll. It actually will just slide down the inclined plane. The only reason things roll, so like if you put an object in an inclined plane, the only reason it rolls, friction puts a torque on it. Friction actually applies a force at the bottom of the wheel, and so the wheel will end up rolling because friction pushes this way, which causes the rotation, and that's the reason things roll. So, there you go. No friction, no rolling. It would just both slide down. And in which case, it doesn't matter the shape of the object. So it's just an interesting question. You know, friction's always bad, y'all. Like, even in this case, friction, while yes, it's better than if you had the block with friction and you had the sphere with friction, the sphere is going to win. But the sphere means some of the energy gets stored in this as opposed to this, which isn't like a bad thing. It's just a thing. There you go. All right, great. There you go, rotational kinetic energy. It's the energy stored in a rolling object. You don't get it for free. If something is rotating, it had to get that energy from somewhere. Nothing is free. And it's the same exact setup as kinetic. It's 1/2 I omega squared. And if you really want, reminder to you all, that V equals R omega. So if it's rolling without slipping, you can actually swap that in, and that does things for you. But yeah, this is the last energy term that I give you all. It's the last thing you have to keep in mind when you are solving energy problems. You had to ask, is it above or below zero? That's gravitational. Is there a spring? Is it moving? And now you have to ask yourself, is it rolling? If it's rolling, there's energy stored in that. There's actually, there's stuff called flywheels. Flywheels are a giant hunk of mass that you spin up, so it stores energy. A flywheel's sole purpose is to store a bunch of energy, and that can be used in a variety of ways. What's another analogy for this? You know, if you have a tire spinning, it's got energy, it's hard to stop it. Like, if something's spinning, I can't just like poke it and it comes to a stop immediately. If you have a tire spinning in the air, you know, you gotta put some work into it to stop it. It's got energy. You can do stuff with it. Spinning stuff is extremely useful, and there's all sorts of reasons why you'd want to store energy as a spinning object. Yeah. Yeah. So why would you ever use this like V equals R omega? If something's rolling without slipping, if you know how fast it's going, like linearly, you can actually swap this in. So like if I give you a problem and I say a wheel is moving with a velocity of 5 meters per second, find its rotational energy. It's just another way to solve this problem. It's just I didn't want y'all to forget that relationship existed. Angular velocity and linear velocity, there's a relationship between them. This is only true if it's not slipping. This is only true like if you have like a tire rolling along the floor. You can only do that swap if it's not slipping. If you can say that yes, Every time it makes one full revolution, it actually moves one full revolution. If it's slipping, so there's a really, I guess the easiest example. If you have a tire spinning on ice, the velocity of that tire is 0. But it's spinning. So you take like the extreme example. If a tire is just spinning on ice in place, the velocity of this tire is 0. Because it's not moving. But it still has angular velocity. It would have centripetal acceleration and stuff like that. Yeah. So I'm actually, to not confuse people too much, that's just gonna, But just remember that can exist. If you have something that's slipping or not slipping, you can do that. All right, look, a blank slide for reasons. Okay. Let's see if this makes sense to you all. I love these problems so much. Two spheres with the same mass are rotating at the same angular velocity. Sphere 1 has half the radius of sphere 2. How does the kinetic energy, the rotational kinetic energy of sphere 1 compare to sphere 2? Is it 1/4 that of sphere 2? 1/2? 2 times it? Or 4 times it? Remember, you all, you can try to do this in your head. I don't super recommend, you're probably going to make a mistake if you do. Write the equation that relates to the variables that you care about. Write the equation that relates to the variables you care about. Solve for the variable that you're interested in. We're interested in rotational kinetic energy. And then change what changes. In the equation, whatever is changing between these two objects, put that change in there, pull it all out to the front, and it tells you the difference. So I'll show you that in a second, but try it out. Your intuition may or may not be right. It's not like a trick question, but I see people mix up these. If the answer is 2 times, people often put 1/2 and vice versa. So. All right, I'm going to give you 30 more seconds. All right, give you like 10 more seconds to take your shot, take your guess. All right, in 5, 4, 3, 2, 1. All right, so again, this is the key. You start with the equation, and I want to compare kinetic energy. So I solved this equation for kinetic energy rotationally. It's already done. Yay, it's already solved for us. It's already solved in terms of that. Now, what is changing in this problem is that R1 is half of R2. That's our nice little relationship we'll just kind of recognize. What's different about them? The radius is. Then we look at our equation, we say, but there's no radius in that, so we rewrite it. We rewrite this where we actually put the term for I in there. There it is. Woohoo. Now R shows up. And so let's say this is the kinetic. If we want to compare 1 to 2, we're going to say, let's put this one as 2. This is the rotational kinetic energy of object 2. We're going to put a bunch of 2's next to everything. Then we're going to write the exact same expression, but for object 1. 1/2 times 2/5 times m1 times r1 squared times omega 1 squared. Great. And then we're going to put object 1 all in terms of object 2. All the variables. So we know they have the same angular velocity. So that's just the same. We don't actually need to clarify that. We know they have the same mass. So we're just going to swap that mass because it's the same mass. And the last swap that we need to make this a little bit more clear, I'm just going to rewrite the whole thing down here. So we're going to do all the swaps. So the mass, they're the same. So we just swap that out easy peasy. The angular velocity is the same. So swap that out easy peasy. The last one you got to do, that looks weird. R2 over 2. We swap in how the radius changes. All right. We then only pull out the numbers that changed. We only pull out the numbers that changed. We do not pull out the 1/2. We do not pull out the 2/5. We only pull out this 1/2 that gets squared, which is going to be 1/4. Why do we only pull out that 1/2 that gets squared? Because if we look what's left over, if we look at what's left over, it is the kinetic energy of object 2. So this is the key. You just write the equation, you put in what changes, you pull it to the front. How do they vary? It's 1/4. 1/4.
Did you square the R2 over 2?
Yeah, so the one thing I did here was, I forgot to put the square there. Thank you. Square. Yep, there was a square there, so that 1/2 gets squared, it gets a 1/4.
Oh, then are we also just seeing the 1/2 in the highlighted section?
Yeah, thank you. Good catch. There is a 1/2 tucked away in here that I forgot to put. 1/4 times 1/2. And I need all my parentheses. Which looks so crazy, but if I erased a bunch of these numbers. Long story short, just put in what changes, pull it to the front. If the mass doubled, you put a 2 in front of the mass. If the angular velocity tripled, you put a 3 in front of it and square it. And then you say, what's the new energy? So let me do a quick example of that just to show you. So same exact problem. I'm not going to make it a clicker one because I just want to go quick real quick. Just to show you how easy these are once you get used to this process. 2 spheres are rotating. 2 spheres are rotating. If sphere 1 has half the radius of sphere 2 and triple the angular velocity and 1/4 the mass, how do the rotational energies compare? And you're like, oh my gosh, it's so many things. You just do the exact same process. Kinetic energy rotational equals 1/2, 2/5, mr squared, omega squared. Then you just swap in all the things. The mass got 1/4. The radius got 1/2. The velocity got tripled. And then you just pull all the numbers to the front. You pull all the numbers, so we pull that 1/4 to the front from the mass. You pull the 1/4 out from doing the square. You pull the 3 squared out, that's going to be 9. That's really hard to see. But this is how you can solve every single one of these. It's really nice. There it is. 3 squared. All right, and you're left over with all the rest of the junk. 2/5 mr squared, omega squared. Long story short, it's 9/16. Ta-da. So you put in all the changes, pull them all out to the front. Ta-da, that's the new one. You can see it's really easy for these to get not intuitive at all. Gosh, you try to do that in your head, good luck. It sounds awful. When you write it out, it's really a straightforward process for how to do this. So, check this out. Try it for yourself. It's a good one. Sake of time, we got just a few more things. Again, we're nearing the end, y'all, as weird as it seems. I'm going to go through this one fairly quick. A neutron star of mass 2 times 10 to the 30 in radius 10 kilometers has a period of 0.02 seconds. What is its rotational kinetic energy? So we got mass. This mass is stupid big. This is the mass of the sun. 2 times 10 to the 30 is the mass of the sun, 1,000,000 times more than the mass of the earth. The radius of a neutron star, specifically this one, is just the size of a city, which you may be like, that's big. Yeah, compared to planets, that's not very big. You have the mass of the sun and something the size of a city. It's neutron stars are the densest objects in the universe other than black holes. And then you got the period, 0.2 seconds, and we're solving for rotational kinetic energy, which is a really straightforward equation. It's the one we've been using, 1/2 I omega squared. Now, in this case, if this is a problem on a test, I would tell you the moment of inertia for a sphere is 2/5 mr squared. A neutron star is a sphere. Just like everything else that's kind of out there. And you look at this equation and you say, what do I got? I got m. Yay. I got r. Great. Angular velocity I don't have, but I do have period. That's the time for one full spin. So I want you all to spend 30 seconds. How the heck do I go from period to angular velocity? All right, and the grand reveal, it comes from literally the definition of omega, the basic definition. What is omega? It's a change in angle over change in time. So, if my period is the time for one full revolution, how much of an angle do I cover in that? 2 pi. There it is, in all its wonderful goodness. So we just plug all this in. So the rotational kinetic energy is going to be 1/2 times 2/5 times 2e30 times 10e3 squared times 2 pi over 0.02 squared. And we're going to get a stupid big number. When you're working with planets, that tends to happen, but neutron stars are especially crazy in their own ways. And you get 3.95 times 10 to the 42 joules. A number so stupid big that you can't really imagine how stupid big it is. Neutron stars, really cool. I'm not going to be able to teach you all angular velocity or conservation of angular momentum. We don't have the time, clearly. We've got 30 minutes left. But there's a really cool thing here. This thing is rotating insanely fast. You have something with the mass of the sun, and it rotates 50 times in 1 second. And it's like, where is that coming from? It's actually a really easy thing to explain. You all know the whole ballerina thing when you put your arms out and spin, and you bring them in and spin faster. That's what happens here. The star was massive. The star was absolutely massive, and when it collapsed to a neutron star, its radius got really small. So the sun is spinning, and when it shrinks to this size, it spins faster and faster and faster, just like when you bring your arms in. If you're already spinning, you'll spin faster and faster and faster. It's conservation of angular momentum, which is kind of cool. These things spin wicked fast for a planet. All right, great. Last thing, and we're going to kind of lightning round through these questions so I can actually do the last problem at the end. So, just to make sure, see, this is going to see if you're paying attention. Remember that if you can know the rotational analog for the linear things, it makes your life way easier, so let's just practice it. When it comes to rotation, what's the analog for F? Is it F, tau, P, or Kr? Obviously, those stand for things. See if you remember what they stand for. A force results in an acceleration. Which of these results in an angular acceleration? All right, 15 more seconds. Again, we're lightning rounding because I got to get to this problem at the end. All right, in 5, 4, 3, 2, 1. 0. What? Oh, it broke. Oh, fine. You get another chance. I have no idea why that broke. The physical base was not collecting jack squat. All right. My lightning round. Clicker blew up. Yeah, this is so slow. I ain't got time for this. Where are you, clicker thing? All right. As always, what do you do when something closes? All right, great. So we can go super lightning round, though. While we're waiting for this thing, answer the next. Oh, I hate that. It's stupid clicker. It's got a strong personality. There's no way to minimize it. You can hear me like aggressively clicking this. This question says, what is the rotational analog for mass? That's the next one. You can prime your brain for that one. So there you go. Think about that one while I'm opening clicker again. Because that one we're going to also go lightning round. Just like this last really quick lightning round. So good. All right, back to this one, which I'll fix things at some point. Does it work? Yes. All right, 20 seconds. Just enough time for the people that are watching it online to realize the question closed. All right, 5, 4, 3, 2, 1. Great. All right, what's the analog? It's torque. Did we do it? We did it. Yay! Great. What's the one for mass? 30 seconds. Is the rotational analog for M, F, I, or KR? In 5, 4, 3, 2, 1. The rotational analog for M is I. The moment of inertia. How is my mass spread out? Remember, it's hard to rotate things that are the mass is far away. So a reminder to y'all, I is the integral of R squared dm. So much fun. Boop, boop, boop. All right, so what? What's the point of this? Well, if F equals ma, and I've said this a few times, then just swap them in, y'all. Torque equals I alpha. If there is a net torque, an object will spin faster or spin slower. If there is a net torque, it will spin faster or spin slower. It is very, very important. Actually, I'm going to just make this a quicker question. After this, I'm going to ask a question to see if you understand regular force. So I'm going to skip the next two clicker questions because I'm going to make my own that I think are more relevant. So torque net equals I alpha, where I is the moment of inertia, alpha is the angular acceleration. It's like F equals ma for a spinning thing. All right, so here's the problem. An object experiences a force of 10 newtons. Is it speeding up, slowing down, not moving, or not enough info? Speeding up, slowing down, not moving, not enough info. There you go. I'm very happy with these responses. Twenty more seconds. And 5, 4, 3, 2, 1. All right, what's the answer? Actually, I'm very, very happy with how this went. I thought it'd go worse. Not because I doubted you all, but because it's a classic. Not enough info. Why is it not enough info? This just says I'm accelerating. But just because I have a positive acceleration does not mean I'm speeding up. A positive acceleration just means my velocity is increasing to the right. If you're going to the left, that means you're slowing down. If you're going to the right, that means you're speeding up. Just because you have a force, that does not tell you how you're moving. So, let's do another one like this. An object experiences a torque of 0. And the units for torque come from the math. It's just M. Let's see, it's I, alpha. Let's just do the easy one. Newtons times meter. Newton meters. An object experiences a torque of 0 Newton meters. What is the object doing? Is it spinning faster? Is it spinning slower? These are not great terms, but it's the best I could think of. Is its angular velocity increasing? Is its angular velocity decreasing? Is it not spinning? Or not enough info? All right, give you all 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, so to understand this, let's write the equation. Torque equals I alpha. If torque is 0, alpha is going to be 0. That's angular acceleration. So what does that tell you about this? Not enough info. Just because your acceleration is 0 doesn't mean you're not moving. Acceleration is not velocity. Acceleration is not velocity. Acceleration is whether it's increasing or decreasing. And that's the thing I don't want you all to get mixed up. Acceleration is whether I'm spinning faster or slower. This thing it's spinning at a constant rate. It's spinning at a constant rate. That rate could be 0 or it could be any number. So, this is always, and this is also true of force. If the force is 0, what is the object doing? It's not accelerating. That's literally all you know. It's not getting faster. It's not getting slower. It doesn't mean it's not moving. So, good reminders. Now, we're going to skip these ones. We're going to skip these ones. I do want to remind you all just of the same thing you all did with forces. Remember, you all add the forces and it equals MA. With torques, we're going to add the torques and it's going to equal I alpha. That's going to be our bread and butter. So this problem is one that looks simple, and it's actually, the setup's not terrible, but there's a little trick in it. I made a mistake, so the reason I like this problem is because as of 5 days ago, I was solving it incorrectly. And fun fact, if you plug this into ChatGPT, it also has a very high chance of solving it incorrectly. Not because the problem is super complicated, but because it's a really easy mistake that you can make. And when we solve this, I'll give you a chance to make that mistake. Don't worry. All right. I got a pulley. This pulley has a moment of inertia of 2. That's just the value of it. Super easy. I don't even need to calculate it. It's mounted on a wall, and I got some masses hanging from it at various radii. One's at 50 centimeters, one's at 20 centimeters, and it asks what's the angular acceleration. This thing will start to spin, and it will start to spin faster and faster and faster. The question is, what is that angular acceleration? And so I'm actually just going to straight up jump to the step 3. So this is going to be the sum of torques equals I alpha. Just to remind you all, it's like sum of forces equals ma. You all did that a bunch. If you want to find the acceleration, you sum up all the forces equals ma. If you want to find the acceleration for an object like this, you sum up all the torques, it equals I alpha. And then I do need to remind you all that torque is R F sine theta, where R is how far away you are, F is the force acting on it, and the theta is the angle between those two things. Okay? Great. So we're going to write down our givens. We have the moment of inertia of the pulley. That's 2 kilogram meter squared. We then have R1, which is, it's kind of tricky to see here, but it's this. And in fact, I'm actually going to draw it over here. R points in the direction of where the force is. R points where the force is acting on it. So this is going to be R1, and then I'll use a different color for the other side so it's easier to see. This over here is R2. Okay, so R1 is going to be 0.5 meters. R2 is going to be 0.2 meters. M1 is going to be 1 kilogram, and M2 is going to be 2 kilograms. All right. And we are solving for alpha. We are solving for alpha. Alpha equals question mark. So yeah, we're going to find the torque that each object causes on it. So long story short, we're just going to torque 1. And I'm going to write this as torque 1 plus torque 2. And then I'm going to pause for, so torque 1 plus torque 2 equals I alpha. But I have an important question for you all. Are these torques helping each other or hurting each other? Are they both trying to make the object rotate in the same direction, or are they kind of fighting each other? So yeah, you all like seeing stuff like this. If you got two things pulling down, one's trying to make it rotate. This guy over here is trying to make it rotate clockwise. Master one's trying to make it rotate counterclockwise. They're fighting each other. We have to make a decision. We have to decide what positive is. And remember, this is going to be, what is the direction? How do we find the direction of torque? That's something that we got to remember how to do. So remember, torque points, if we have a R like that and we have an F like that, this is the right-hand rule. See if y'all can figure out what is the direction of torque. If you have R pointing to the left and F is pointed straight down, right-hand rule, what's the direction of torque? Yeah, so remember y'all, you put the hand in the direction of R and you swing it towards F and your thumb points out. The other way you can do this is you can just say which way is this going to want to accelerate. The force is going to make it go counterclockwise, so you just, do that. Make your fingers counter. And so this torque is out. So we'll call this torque 1 and it's out. And then the other one, the torque 2 over here, F2, that torque is going to be in. Let's define out of the page as positive because we can. Therefore, these are vectors. So we're going to subtract that torque from it. Great. At this point, things are maybe looking like, you're like, great, we got R, we have I. This angle here is the angle between the force and the radius. In both cases, these are 90 degrees. Pulleys always operate with a 90 degree. So this angle is going to be 90 degrees for both of them. Yay, that's just one. Very nice. And now we're going to get to the point where the mistake will happen. If you don't believe me, well, we'll see. Maybe you'll realize it. Maybe you won't make the same mistake I and ChatGPT did. So let's write this out. So we have R1 times F1 plus R2 times, let's put the negative in front of that. So my question to you all, and I'm going to go ahead and straight up tell you, this is where the mistake will happen if it happens. What is the force? What is the value of this force? So spend like 30 seconds on this. This is, if you think of the answer in 10 seconds, you're probably wrong. How do I find these forces? Spend some time thinking about it. If it takes you less than 30 seconds or less than a minute, you're almost guaranteed to be wrong. All right. So now that you've had some time to think about it, if you said that the force is mg, it's not. That's right. I told you if it's like and that's the mistake I made. I said that this force was just m times g, and I'm going to show you why that's not true. We're going to figure it out together. This force is a string pulling on something. What's the name for a force of a string pulling on something? It's got a special name. Tension. Very nice, y'all. So this is force tension. Now, how the heck are we going to find this force tension? Well, we don't have enough information at the pulley side, but we know Newton's third law. For every force, there's an equal and opposite. So the tension that's pulling that thing up, we're going to draw a free body diagram. So let's just look at this over here. We're going to draw a free body diagram of this. We did it. So the force of tension, we can just put it as T. Let's just relabel this as T now that we know what it is. T1 minus M1 times G equals MA. And then the mistake here happens, and this is the mistake I made. I was just like, oh, T equals MG, done. That's only if A is 0. But if A is 0, this thing doesn't accelerate, and the whole problem, the answer is 0, and what's the point of doing the problem in the first place? This thing is accelerating. A is not 0. A is not 0 in this problem. They are accelerating. Gravity's pulling them down, and so they are accelerating. So let's write this for the other one as well. I'm going to use both terms, and I'm actually going to put an A1 here. So T2 minus M2 times G is going to equal MA2. Okay. And then you're like, what? Now I've got an A in here, and I've got to figure out an A. So how are we going to do that? We're going to remember that there's a relationship between angular and linear. Remember, y'all, that, and I'll do this in a different color, A equals R times alpha. How do you go from linear to rotational? And we're going to see the benefit of this. So A1 equals R times alpha 1. And therefore, A2 equals R times alpha 2. So we can write those out. Boop, boop. So T1 minus M1G equals M1 times R times alpha 1. And we get T2 minus M2G equals M2 R2 times alpha 2. And there's one last thing we have to do to be careful. There's one last thing we have to do to be careful.
Which way the alpha is?
Oh, yeah, it is going to be related to the direction of alpha. I don't want an alpha 1 and an alpha 2. I don't want two different alphas. They're both going to share the same alpha. But the problem is alpha 1 is not going to be the same as alpha 2. And it's going to be simple to show that if you just look at these blocks. If block 1 goes down, which way is block 2 going to go? These accelerations have to be opposite signs. These accelerations have to be opposite signs. Why? Because again, if one goes down, the other goes up. So I can't say alpha 1 equals alpha 2. Instead, what I have to do is I have to say alpha 1 equals negative alpha 2. Okay? And that's going to let things actually work out for us. If we don't do that, everything goes south and it's awful. All right. So finally, we're going to start to put the things together and close out this problem. And make certain I did all my negative signs correctly and all that stuff. So I'm just going to steal this bottom. It takes a lot of writing, but that's the reason. This problem is a good problem, and there's going to be a problem like it on the quiz, so be prepared. But the final result is actually really simple. When I show you all the final result, I'm going to show you there's a shortcut to this problem. So that's going to make your life better. We're going to get there when we get there. So, this is going to replace with tension. Tension. So, tension 1. Where do I want to write that? We'll just do it over here. Tension 1 is going to equal M times R1 times negative alpha plus M1 times G. T2 is going to equal M2 R2 times alpha. Just alpha plus M2 times G. And then we just plug those in to the equation. So what color is that going to be? Let's do green. So now we're going to take these and put them in here. All right, so we're going to get R1 times negative MR1 alpha plus M1G plus, we'll just make this a minus, R2 times M2 R2 alpha plus M2G equals I alpha. And you're like, oh my gosh, so many things. This last step, y'all, it all comes together nicely. It's all going to come together. You're looking at this like, oh, that's so much. Kinda. It is. In some ways. Then we just write it out. So we get negative M1 R1 squared times alpha plus M1G R1 minus M2 times R2 squared alpha minus M2 times G times R2 equals I alpha. It's just distributing it. And then you get all the alphas together. You get all the alphas together. So there's alpha, there's alpha, there's alpha. So we're going to get I alpha plus M1 R1 squared alpha plus M2 R2 squared alpha. We're getting really close to where I can show you all the shortcut, which is nice. M1 G1 R1 minus M2 G R2. And finally, if we pull out the alpha, we get I plus M1 R1 squared plus M2 times R. Yeah, I don't got room for that. Squish. Here. All right. Almost there to the part that if you realize this part, the rest of the problem is really, like, it's easy to do a problem like this in the future. Alpha times I plus M1 times R1 squared plus M2 times R2 squared equals M1 GR1 minus M2 GR2. Okay, and you're looking at this to be like, how is, like, what's easy here? If you look at this term on the left side, I plus MR squared plus MR squared. If MR squared is somehow ringing a bell in your mind, that's a good sign. Reminder to you all, I is the sum of mr squared. So this problem is effectively just an object. We just added up all the moment of inertias. So we basically pretend like this problem is just these masses are kind of just chilling up here. And to that end, it ends up just being a problem of I alpha equals the torque, and the torque equals what you wanted it to be in the first place. Which is kind of nice. So you get I times alpha equals the torques that you originally wanted in the first place. This whole big term here in purple is basically just I. And then the term on the right is just a bunch of torques. And you just divide and you're done. So, boom, boom. Copy all this nonsense over, do the last part, and call it a day. The final part's just plugging numbers in, the least exciting part. So yeah, please, please, please make certain you all can do this problem. Because pulleys are a classic. And you got to account for this stuff. Unfortunately, it's not something you can ignore. 1 minus M2 GR2 all over. Just add up all the i's. M1 R1 squared plus M2 R2 squared. And yeah, the numbers here are actually really nice. Like, they're really easy to plug in. M1 is 1. So it's 1 times 9.8 times 0.5 minus 2 times 9.8 times 0.2 all over 2 plus 1 times 0.5 squared plus 2 times 0.2 squared. And you do all that and you get 0.42, I think, something like that. Yep. The reason I like this problem, y'all, is it makes you use both of Newton's. You get to use the torque equals I alpha and F equals ma, and you need both of them to solve the problem. Yes, it's a good amount of steps to it, but make sure y'all can do it. Once you kind of write it out, really the only tricky part was realizing that the accelerations are negative of each other. Part B I didn't do, but it's really easy. Part B says find the linear acceleration. I'll give you all 10 seconds to see how do I go from rotational acceleration to linear. A equals R alpha. You just multiply this by the radius of each object and you get the acceleration it experiences. That's it. So these are in the thing, but if you do 0.42, 0.42 times 0.5, you get 0.21 negative. Let you figure out why it's negative. And A2 is going to be 0.42 times 0.2. And that's positive. Super simple. And A2 is going to be R2 times alpha. Yay! All right, great, done. We did it. We covered everything. Clearly we didn't have time for angular momentum, but torque is half. If you take statics, it's half the class. Torque equals I alpha is half the class. F equals ma is half the class. So I had to get through it. Yep.
Like at the bottom of the sum of all the
The eyes?
of inertia.
Yeah, yeah.
So like how would you do